Buenos días, buenas tardes. A nombre del Consorcio de Universidades por la Ciencia, el Colegio Nacional y Fundación UNAM, les damos la bienvenida y les agradecemos el interés en este ciclo de conferencias. El ciclo es organizado por este grupo de universidades en México y también en el extranjero, en Estados Unidos, en Inglaterra, España, Brasil, y está dedicado a la presentación de estudios que están en desarrollo, de investigaciones que están avanzando, y eso es lo que ha caracterizado a este ciclo. El día de hoy tenemos una conferencia muy especial a cargo de la doctora GAIL CHRISTESON de la Universidad de Texas en Austin. La doctora GAIL CHRISTESON es investigadora en el Instituto de Geofísica y en la Jackson School of Geosciences in the University of Texas, y es la directora adjunta en el instituto. La doctora GAIL CHRISTESON es una especialista en geofísica marina y ha realizado una gran cantidad de investigaciones de cruceros y ha trabajado durante mucho tiempo en el Golfo de México, en la estructura cortical del Golfo de México, la formación de la corteza y cómo se origina el Golfo de México. Y ha hecho estudios en muchos otros lugares, estudiando la corteza y la tectónica en muchas otras regiones. La conferencia del día de hoy se centra sobre uno de nuestros sitios geológicos únicos, que es el cráter Chicxulub en Yucatán, y que se forma por el impacto de un gran asteroide hace 66 millones de años. Y los efectos de este impacto causaron la extinción de alrededor del 75% de las especies. 3 de cada 4 especies que estaban en esa época, incluyendo grupos grandes como los dinosaurios, se extinguieron, y este impacto marca el fin de una de las eras geológicas. Entonces es realmente un gusto y la doctora tener esta conferencia, y la doctora CHRISTESON ha sido una de las especialistas más activas que tenemos en el estudio del cráter Chicxulub. La conferencia es sobre el mapeo de lo que se conoce como la estructura del Peak Ring, que es el anillo de picos, y vamos a ver la enorme, la gran resolución que tienen los datos geofísicos, y que es la especialidad de la doctora CHRISTESON. Dr. GAIL CHRISTESON, thanks very much for accepting the invitation. It's a real pleasure to welcome you, and we hope to see you soon in Mexico City. And the conference series is organized by a group of universities with the Colegio Nacional and the UNAM Foundation, and is but the main characteristic of this conference series is that it's on research being done. It's the main characteristic, and this is a pleasure to have you and to have this presentation on the Chicxulub impact. The Chicxulub is one of the unique geological sites we have in Mexico, and you are one of the most active researchers, and we really appreciate your participation, and also appreciate your friendship so many years. For the conference series, we have recently the addition of the public universities in Mexico, the ANUYES, and the Secretary General of ANUYES has asked us to also welcome you and thank you. And tenemos el presidente de Fundación UNAM, licenciado Dionisio Meade, y la directora ejecutiva, ARACELI Rodríguez de Fernández. Nuevamente les agradecemos. Al final tendremos oportunidad de tomar unas preguntas y nuevamente pues un gusto estar con ustedes el día de hoy y le pasamos la palabra a nuestro presidente de Fundación UNAM, licenciado Dionisio Meade. Gracias. Thanks very much.
Muchas gracias, Jaime. Muchas gracias a todos por acompañarnos otra vez en una presentación de este consorcio de universidades que ha significado una formidable respuesta frente a la pandemia para no detenernos en nuestra marcha por la investigación y por el desarrollo de la ciencia. Nos hemos vinculado de manera muy activa y hemos logrado algunos beneficios que no imaginábamos. Mientras que algunas de nuestras pláticas al principio significaban una participación de un auditorio de 80, 100, 200 gentes, hoy a través de las redes lo que hemos podido apreciar es el interés que se genera no solamente ya en América, sino en otras partes del mundo, una experiencia casi transoceánica como con las participaciones que hemos tenido de expertos de otras universidades de Europa y que ahora tenemos también pues con la participación de GAIL, que nos hace favor de presentarnos también sus investigaciones y sus avances de la Universidad de Austin. No es la primera vez que tenemos una presencia de esa universidad y esto va acreditando cómo se va generando un andamiaje, una fortaleza, un espacio en el que se comparte la investigación, pero en el que se suscita también la inquietud y el interés de que otros estudiantes, otros académicos de distintas partes del mundo se vayan sumando a lo que va resultando de estos esfuerzos en donde se participa y se comparte la investigación. Creo que estas lecciones de la pandemia pueden derivarse en los elementos positivos que están derivando de una circunstancia como la actual. Y otra sin duda, porque la gente ha cobrado conciencia de eso, es la protección del planeta. Conocerlo mejor, saber mejor sus orígenes, saber mejor cómo lo tenemos que cuidar, es un desafío muy relevante. Yo mismo tuve la experiencia de acompañar a Jaime Urrutia en una visita precisamente a Chicxulub y precisamente que consideramos que si usted ya lo hizo, pues cuando venga a México, venga también a la capital, pero también realice este viaje para visitar en el sitio propio lo que nos enseña Chicxulub. En esa oportunidad tuvimos manera de conocer esto que ahora menciona Jaime, que es tan importante. El 75% de las especies desaparecieron con la caída de ese meteorito y tuvimos la oportunidad en ese viaje de ver en el buque de la universidad que transitaba y que llevaba a todos los expertos de muy distintas partes del mundo a tratar de conocer qué fue lo que pasó, qué especies habían ahí, qué se podía recuperar de lo que entonces se podía investigar, en un esfuerzo inédito en donde el idioma no era una barrera, en donde investigadores de muchas partes del mundo, como ahora se puede lograr con el consorcio, se estaban sumando a esta participación. Fue para mí en lo personal una experiencia inolvidable que nos suscitó inquietudes, que nos suscitó deseos de conocer más la historia de nuestro planeta y que nos sigue inquietando. Siempre nos preguntamos si habrá la posibilidad de que nos vuelva a caer otro meteorito. Ojalá nos pueda decir GAIL algo sobre esto. Y queremos dar también la bienvenida porque para nosotros es una gran noticia que esté presente un representante de la NUYES. La NUYES coordina la presencia de muchas universidades del país y hoy que se sume a este consorcio es para nosotros una gran noticia. Bienvenido la NUYES, saludas a Jaime Valls, es su presidente, gran amigo mío, y que compártanle por favor el gusto, la satisfacción que nos da que se sume a este esfuerzo. Muchas gracias a todos y deseamos pues el mejor de los éxitos en esta presentación que escucharemos con enorme interés. Gracias a Jaime, gracias a la Universidad de las Américas, gracias a todas las universidades del consorcio, gracias en esta ocasión a NUYES por sumarse al esfuerzo y gracias a la Universidad de Austin que otra vez participa activamente compartiendo su experiencia, su conocimiento con la presentación que nos hará favor de hacer GAIL el día de hoy. Muchas gracias a todos.
Gracias, thanks very much. And Dionisio was telling us that he went to the drilling platform. So he had the opportunity to see the drilling operations in the big ring in Chicxulub, and that he very much enjoyed. And he was also, well, reiterating our invitation to you, Gail, to come and visit us, we hope soon. And with this, we will have the conference by Gail Christensen. Thanks very much, Gail. And we hope you enjoy this presentation that will illustrate the studies we have been doing, part of a large international collaboration, particularly or especially with the University of Texas at Austin. Thanks very much, Gail, and please.
Okay.
Go ahead.
Okay, so if you could just confirm everything looks good.
Everything is okay.
Okay, thank you. So thank you for the kind invitation. So today I'll be talking about the Chicxulub impact structure, and I'll be giving some background information, and then I will be focusing on some of the research that I am doing together with collaborators. So here are just some images to get us in the mood to look at the Chicxulub impact crater. So we'll start with some background about impact craters. So impact craters, their morphology, so their shape and features changes as the size of the crater changes. So if you have a small impact, you will just get a simple bowl-shaped crater like the meteor crater in Arizona, shown here on the left. As the impactor size increases, you will excavate more material, and you excavate so much material that you actually get a rebound effect. So at the center, you will get what we call a central peak. And then for larger craters, which Chicxulub crater that I'm talking about is one of these, you remove so much material that this central peak is so large that it collapses, and you form what we call the peak ring. So this is the feature I'll be focusing on during this talk. And just some other terms that I will mention. So this is the peak ring. In the center is what we call the central basin. This is the crater rim around the outside. And then in between the peak ring and the crater rim is what we call the annular trough. So some background about the discovery of the Chicxulub impact crater off the Yucatan. In 1948, this zone of concentric anomalies was discovered in gravity data. So this is gravity data over the impact site. And that started an exploratory drilling program because circular features are often traps for oil and gas. And this program was completed by the mid-1970s. And the program found unusual crystalline rocks and breccias. And at the time, these were interpreted to be part of a large volcanic field. But in 1980, Alvarez et al. Proposed that the extinctions at the KPG boundary were caused by an impact. And soon thereafter, Penfield and Camargo proposed that the Chicxulub structure could be a buried impact crater. So building on this, in 1985, there was a discovery that a sandy bed in Texas at the boundary could be a tsunami deposit. And this suggested that if there was an impact at the boundary, it would be in the Gulf of Mexico or the Caribbean. And then in 1991 and 1992, papers were published naming this Chicxulub structure as the KPG impact basin. So I actually got involved in this 1997 part of the timeline when there was a publication of seismic data imaging the Chicxulub crater subsurface. So what is the evidence correlating Chicxulub with the KPG boundary? So here we see the KPG boundary in Europe. So here it's a thin clay layer. But as you get closer and closer to the Gulf of Mexico, that impact layer changes. So here in Spain, there's a very thin impact layer, such as pictured here. But these intermediate sites, which are shown in orange on this map, so in North America and parts of the Caribbean, you can see that the impact deposit is getting thicker. And then these proximal sites, so these kind of ring the Gulf of Mexico, the unit is much thicker, and you start seeing this high energy unit, which we now know is the tsunami deposit. And as you get closer to the impact site, so here in Mexico, you get a very thick layer, and at the top of the layer is where you find the iridium anomaly that we've all heard so much about. And here's just another image on the right showing the changes at the boundary before the impact, the way the fossils appear versus after the impact. So there's just such a big change in the fossils, and this is marking the extinction. So here is an image over the crater itself. So this is the seismic data that we acquired in 1996 and published in 1997. And what you can see is the y-axis is time. So this is showing, in effect, what depth in the subsurface. And as you approach the crater, the subsurface starts getting disrupted, and you see these faults that are interpreted. And then you get into the crater itself, shown here. And these wells that had previously been drilled by Pemex are projected onto here. And so here you can see the T stands for the tertiary, so the post-impact sediments, and the B are the breccias that were drilled, impact breccias. And then this feature here, where you can see this uplift, that is the peak ring. So it doesn't look that drastic on this type of scale, but these are hundreds of meters of relief forming the peak ring. And if we look deeper, here we are looking all the way to the base of the crust at 35 kilometers. All these, what we're seeing is a line drawing interpretation of the seismic data. But what we see are faults that extend all the way to the base of the crust at 35 kilometers depth. So you can just imagine the energy of this impact. And even at the base of the crust at 35 kilometers depth, we see that the interface between the crust and the mantle, which we call the moho, has been uplifted by 1.5 to 2 kilometers at the crater center. So that's a bit of background about the crater itself. So let me talk to you about the drilling project. So the peak ring was drilled on what we call Expedition 364. We used this platform shown here. So there were 2 phases. There was the offshore drilling, where only a small group could participate because it's a very small platform. And then all of these rocks were transported to Germany. And then we had a much larger science party where we're able to examine all the rocks and describe them. So here again is an image showing drilling of the peak ring. And on the right, we can see what was recovered. So this is the lithology. And then we see some photos. So the upper part that was drilled is sedimentary rock. So this is post-impact rock. Then we went through a section of what we call swevite, which is a melt-rich breccia. So the impact melt happens because the pressures are so high that you melt the rock. And then that forms this breccia that we're seeing here. So all of these examples. And as you get deeper in the section, these clasts get larger and larger. So it's really quite spectacular looking at these rocks in person. Then there is this thin layer of impact melt. And then the rest of what was drilled is this crystalline basement, which was fractured granite. Okay, so that's an introduction. Now I'm going to move into talking about what we learned about the Chicxulub peak ring. So here are some images of the material we recovered. There are shocked quartz, and there's a brittle faulting. And here you can see lots of little faults. Here's some of the melt rock. So the shock metamorphic features indicate that the peak ring rocks were subjected to shock pressures of 10 to 35 gigapascals. And the impact melt requires pressures greater than 60 gigapascals. We also measured the physical properties of these rocks. So that's what's shown here on the left. So we measured the P-wave velocity of the rocks and the porosity, among other measurements. And if we focus in on the granite, which is what forms the peak ring, what we find are that the velocities are very low compared to normal granite. So normal granite will have velocities of 5,800 to 6,500 meters per second, but the rocks that we recovered have velocities of 4,100 meters per second. So extremely low for granite. And there's also very high porosities. So granite usually has very little porosity, less than 1%, but we measured porosities of 8 to 10%. And you can see what's forming the porosity. There's just lots of fractures in the granite. Here is a photomicrograph, so showing at the much finer scale all of the fault, all the cracks that are happening in the granite. So this is just a reflection of the high pressures that occurred. So using these results, our group was able to verify a model for how a peak ring forms. So that's what we're seeing here on the left. And on the next slide, I'll show a little movie showing this in action. So we have the impact happening. And then here we can see the time. So in 1 minute, you start forming what we call a transient cavity. So you started excavating this hole in the ground. And then in 3 minutes, you start getting this central uplift. And here you can see the crater rim is starting to form. And then that crater, the central uplift collapses. The rim also is starting to collapse. And you start forming this peak ring. And so within minutes, so this is showing at 10 minutes, the peak ring has been formed. So extremely fast process. And the peak ring rocks that we drilled originated at 8 to 10 kilometers depth and moved more than 20 kilometers. And here is a video showing the whole process. So here you can see the central uplift and the rim being formed. Then the rim is collapsing, and then the central uplift collapses and the peak ring is formed. So the part that the research I'm actively working on right now is using seismic data. So the drilling let us recover rocks from one point in the crater at the peak ring, and then we can use geophysical data to map around the crater. So using what we learned by the drilling, then we can integrate with the geophysical data and map features around the impact crater. So what I'm showing here is a gravity map. So you can see these circular features corresponding to the crater. You can see these yellow squares show some onshore wells. Then here offshore is where we drilled into the peak ring. And then these light blue lines are showing the seismic grid. So that's what I'll be using to map features away from the drill site across the crater. So this is a very busy slide, but it's showing in basically one image the method I am using. So it's called full waveform inversion. And what full waveform inversion does is it allows you to produce what we see in color here. So a high resolution velocity model. So how does this work? So we actually take the same data that was used to image the subsurface. The colors are overlaying on the image. So we take the data that's used to create the reflection image. And so that some of the data is shown here. So we take that data and then we create a starting velocity model that we think could match these data. So that's shown in this next panel. So here's the observed data. And here is some data that we've created synthetically with a starting model. And then this bottom panel is showing that we iteratively iterate to create a better velocity model that fits the data better. And we keep doing this until we get a good match. So just a few features that we can look at. So in the observed data, these arrows are showing like this little curve feature here. You don't see it with our starting model, but you do see it here in our final model. And there are some other features that you can see as well. So this is briefly how we create these high resolution velocity models. And this is the second slide I want to show about the method. So this is the data that images the subsurface. So we call that seismic reflection data. We use those same data to get a velocity model. So that's shown here. This reflection image is in two-way travel time. And we use the velocities to accurately convert it to depth. And then finally, we can overlay the velocities on top of the reflection data. And so that's what I'll be showing in the rest of this talk. Okay, so mapping the peak ring. So we've done this previously. And so this is showing a publication from 2013. And what we did was we used the topographic high. So here is some reflection data. You can see the peak ring here. So mapping that topographic high. is shown here on the left. So what we see here is the depth to the KPG boundary that's been interpreted. And the greens and the blues are shallower. The reds and the yellow are deeper. And so you can see, for example, these blues here are close to where we drilled into the peak ring. So there's a topographic high, and then that was mapped as the peak ring. So that's what these yellow, what the white lines are showing. So the edges of the peak ring. If we plot those on top of the gravity shown here, you can see that there's this circular gravity feature, and the peak ring roughly corresponds to that gravity feature. So that's a gravity low. A gravity low is correlated with low densities, and low densities are correlated with low seismic velocities. So you can see here is what was known about the seismic velocities before, and you can see that these velocity contours are depressed underneath the peak ring. So everything seemed to match. We had a topographic high, we had low velocities, which we now know are from fractured granite. We had a gravity low, but you can see that things didn't quite match. So let's look at our new interpretation. So now we have much higher resolution velocity data. And so what we're seeing here are 3 images of the peak ring, where we have the reflection image and the colors are showing the velocities. So here is where we drilled, and you can see that the colors change from these greens to the reds on each side. And we can use those to mark the edges of the peak ring from where we go to green to red. So these are low velocities, and at the edges are higher velocities. So that's how we've mapped the peak ring on this profile. The next profile is a little different in that there's actually 2 topographic highs, but the second topographic high has much higher velocities. And so we know that the peak ring material doesn't extend all the way to the second topographic high. And then this third example is very interesting because there's a topographic high on the right, but then there's this extended region where the velocities are low. And so we think this peak ring material actually extends much further than the topographic high would suggest. And I'll show another image of this on a later slide. So how does our new mapping compare? So these heavy dashed lines show where we now map the peak ring, and there's a very good correlation with the gravity. So shown here. This central image is showing the depth to the top of the peak ring. Well, this to the top of the boundary between the Cretaceous and the Paleogene. And you can see that the peak ring is mostly these blues and light blues. So it's topographically high. And then the bottom image is showing the velocity beneath the KPG boundary. And you can see the velocities are mostly these purples, which are the low velocities. So everything is consistent. The peak ring is composed of low velocity material. It's a topographic high, and the peak ring aligns with a gravity low. And the feature that I want to point out here is that these blues are the highest peak ring, and that's where the peak ring is narrowest. So here in the west where we drilled, the peak ring is narrow and tall. And then over here in the north, the peak ring is deeper and it's wider. So here is that example where we interpret the peak ring to extend further away from this topographic high. And if we overlay this profile on top of the gravity, so that's what we see here. So this is the gravity low. And our new interpretation matches that gravity low. So that gives us confidence that we are accurately mapping the peak ring. And it also has some implications. So if we see this peak ring crater on the moon, you can see that the peak ring is not continuous. So the topographic highs are missing here at the bottom. But perhaps this peak ring material does continue, it's just not a topographic high, as in this example that we see at Chicxulub. Okay, so what's causing the variability in peak ring depth and width? So we, as we saw, the peak ring was tall and narrow in the west, and it was wide and deeper in the north. So there's two things we think are affecting this. Sorry, I'm hearing some noise. So first, we know that where the Chicxulub impact happened, there was actually some pre-existing topography. So there was a deep basin in part of where it hit. And we can see that in the seismic reflection data. So we're looking at the subsurface, and you can see just how this, this reflector deepens here. And this is where the northeast is. So, so here's a little schematic showing in the northwest, we had a shallow basin, and in the northeast, a much deeper basin. So a 1 to 2 kilometer deep basin. So if you model what happens when you have deep water versus shallow water, what will happen is that the ejected material where you have deep water actually forms a tsunami, okay? And when that tsunami comes back in, the crater rim will be washed away. So where you have thick water, so deeper water, the deep basin in the northwest, we don't think there's a crater rim. Okay, so that's one thing that we know is different. And the other thing that we know is different in the Northwest is that the impact is modeled now to come from that direction. So the impact came from the Northwest to the south, the northeast to the southwest, sorry. So this direction here. And modeling of what happens with the impact direction is that in the downrange direction, you'll have more melt and higher shock pressure and a higher crater rim. And in the uprange direction, you have the opposite. You have less melt, you have less shock pressure, and you have less of a crater rim uplift. Okay, so where we drilled, we'd expect to have the higher crater rim, the more shock pressure, more melting. And then in this other direction, in the uprange direction, we'd expect less shock pressure, less melting, and less transient crater rim uplift. So we know that the peak ring forms by the collapse of the central peak interacting with the collapse of the crater rim. So if you have less crater rim, we argue that this will result in a deeper peak ring. And then finally, I think that the tall and narrow peak ring could have the same volume of material as a short and wide peak ring. Okay, so that kind of summarizes what we've learned about the peak ring. Let's look at the resurge deposit. So because we had this deep basin, we created a tsunami, and then the tsunami came back in. And so here are some little cartoons showing, you know, within hours, you're having this material that's from the impact is settling down into the crater. And then you have the tsunami come in and disrupt everything. So closely examining the rocks that were recovered, the swavite rocks, you can come up with a timeline of what actually occurred. And so that's what this very busy slide is showing here. But let's just step through the first day of the Cenozoic. So within minutes, the peak ring formed. And then within tens of minutes, so here kind of in the middle, the peak ring was starting to be capped by material that was ejected and then came back in. And then you start getting the resurge deposit as the tsunami comes back. So, and then in the end, within a day, the tsunami has gone across the Gulf of Mexico and come back in, and it deposits even finer grain material, including some charcoal fragments, which are evidence of impact-induced wildfires. So we're going to focus in on this tsunami deposit, so the resurge deposit. So we can map this because it has a change in physical properties. So when we drilled, we also did some downhole measurements of velocity. And we can see that this resurge deposit has a change in velocity at the top and the base. So it's lower velocity than the material above it or the impact rock and granite below it. So, so it will show up in our high resolution velocity models, and we can map it. So that's shown here on the right. So here we have this low velocity layer that we can map using the velocities and the seismic reflection image. So we've done that. So this, this figure, the colors are showing the thickness of this layer. And it's mostly in this image green. So there's a pretty uniform thickness of the layer at about 187 meters. The thicknesses are similar on the peak ring and in the annular trough, and they're thicker here in the central basin, and we'll explore that a bit later. Let's look at this peak ring, what's going on at the peak ring. So the peak ring was very rugged, but what we see is that the resurge deposit fills in the topography. So here is a little zoom in of the peak of the top of the peak ring. So this is all peak ring. And this light blue is showing the base of the resurge deposit, and the yellow is showing the top. And what we see is that the resurge deposit is thinner where the topography is elevated, and it's thicker at these topographic lows. So it looks like the resurge deposit fills in the topographic lows, and then it drapes the entire surface. See, so this this suggests that the resurge deposit flowed in, so it didn't deposit. It wasn't aerial. It flowed, and again deposited first in these topographic lows, and then over the entire surface. Okay, so let's finish up by looking at the impact melt sheet. So we recovered this really extraordinary impact melt. So here's an example image. So what did we know about the impact melt sheet before drilling? Well, we interpreted this feature that you can see on the seismic reflection data, this low frequency reflector, this is in the central basin. We interpreted that as the top of a melt sheet. So on this image, what we're seeing is the peak ring here. This is the central basin, and the central basin had this, this melt sheet. Okay, so now let's look at our new data. So that low frequency reflector, it doesn't really show up on this image, but it's right here. And beneath it, we see these red velocities. So these are high velocities. So there's a really nice correlation between these high velocities and where we thought the melt sheet was. So what else do we see? So here is the peak ring. Here's the central basin. Here is the melt sheet. And then we see these very odd features in that resurge deposit. So this low velocity layer is very thick in places. And it disrupts the sediments above it. And what we think this represents are hydrothermal upflow zones. So the impact melt sheet is very hot, and there's water in the region. So the water will circulate and set up a hydrothermal system. And because there's so much heat here at the melt sheet, you'll get these upflow zones. And we think that's what we're seeing. So we only see these features in the central basin. And we only see them near where we think this large impact melt sheet is. We can't see the bottom of the impact melt sheet with the data that we have. So some information about the hydrothermal system. It's been modeled, and there's evidence for it in the rocks that we drilled. So there's lots of hydrothermal alteration, as shown here. And here is a model showing the system. So we have our peak ring, we have our central melt sheet. So we have very high temperatures. So here temperatures 1200 degrees centigrade. And a hydrothermal system is set up where there's a lot of upflow near the peak ring itself and then above the melt sheet. And the drilling results provide evidence for a hydrothermal system with high temperatures of 300 to 400 degrees C that persisted greater than 2 million years. And we're hoping we can get a better idea of how long it persisted by trying to correlate, the disruption of these sediments. If we could get an age of that, we could get a better idea of how long the system lasted. So that's the central basin, but we also find impact melt rock in the annular trough and on top of the peak ring. So in the annular trough, we see these high velocities, very similar to what we see in the central basin, except we can sometimes see a base to them. And when we do, it looks like the melt rock is thicker near the peak ring and thins away from the peak ring. So this is in the annular trough. And where we can map it, the thickness, it's about 500 meters thick. Then on the peak ring, so here is the peak ring. Here's that central basin with the large melt sheet. We think we can see a little bit of melt on top of the peak ring in areas. So sometimes you can see these slightly higher velocities. We also see that low frequency reflector. But we think it's very thin on top of the peak ring. And there are no mapped hydrothermal upflow zones in the annular trough or on the peak ring. So the highest temperatures were definitely in the central basin. So what material is between the base of this resurge deposit and the top of the melt sheet? So that's kind of a puzzle because where we drilled, we don't think we've really sampled this material. It's much thicker here in the central basin, and it's thinner in the annular trough. So what we think this might be is we have this hot melt sheet. We have water coming back in, and that water will interact with the melt sheet and form what we call melt water interactions. So the top of the melt sheet could be fractured and turned into breccia by the water coming in. So that could be a lot of what we're seeing here, but we just don't know. But again, this layer between the resurge deposit and the melt is much thicker in the central basin where we have this hot melt sheet than it is in the annular trough. Okay, so that's what we've done so far. A little teaser for a future survey. This is in collaboration with Jaime and León and UT. So we have a funded project with Context for 3D imaging. So some small 3D imaging of where we drilled. And this other site here, and what we're seeing here is this is the gravity data. And this gray line is showing the Progresso Pier. And we plan to survey close to the Progresso Pier. And why would we do this? Well, where we've imaged so far, that line that we saw that showed the nice hydrothermal upflow features, this is as close as we could get to the coastline with the ship that we had. But the center of the crater is right here at the coastline. So what we'd like to do is do a survey near the pier where we can get close to the crater center and image more of the melt sheet. So we'll be using the Justo Sierra and this system that University of Texas has. And what we're hoping for is that this, so the site over the drill where we drilled will help us get higher resolution data and maybe see some of the features that we interpret. But this new site near the pier, we're thinking could be a potential target for future drilling into the melt sheet itself. Okay, so I'm going to summarize now. So what we're seeing is our two cartoons. So here's a map view, and we're plotting the gravity. So we have the peak ring. We think it's continuous. In the west here, it's narrow and high. Here in the north, it's wider and deeper. On top of the melt sheet, we think there's some thin isolated melt that we've been able to map. In the central basin, we have this large melt sheet that set up a hydrothermal system. We see hydrothermal upflow features. In the annular trough, we see some thick melt near the peak ring, and we think we see some thinner melt away from the peak ring. We think that the impact came in this direction. So from the northeast to the southwest, and that could be responsible for some of the differences we see in the peak ring as well as the fact that this is the location of a pre-existing basin. So if we look at a cross section, here is where we drilled into the peak ring. So we have the peak ring itself. So that's shown in pink. We have a melt sheet in the central basin. We have upflow. We have this thick layer that here we've marked as swevite and melt rock. So this could be formed by the water melt interactions. We have the resurge deposit as well. In the annular trough, we also see melt, but it's much thinner. And I didn't show, but it looks like there's kind of a change in velocities between the peak ring and the melt, which could indicate fracturing. We've projected on some of the onshore wells. So Y6 drilled into the annular trough. So this would be in a position close to the peak ring and the melt sheet. And it did encounter some melt. C1 shown here is in the central basin, and it bottomed out into the melt sheet. And then here on the left, we're seeing the crater rim and these sediments that are faulted and downdropped. And then we see this large region of breccia that probably formed from when this crater rim collapsed. So the interaction of that collapse. Okay, so I'm going to end there, and I'm happy to take any questions. And I just want to acknowledge all the members of the Science Party and collaborators throughout the year who contributed to these results. So thank you.
Well, thanks very much, Gail. It's a really very interesting presentation, and it's interesting to see the new results coming from the geophysical survey and the drilling. Thanks very much. We have actually quite a number of questions. I will try to take some of them. Muchas gracias a todos por las preguntas y comentarios. El número de preguntas es muy alto. Vamos a tratar de tomar las más que podamos. We will try to take as much questions as possible, but we apologize for those who cannot be read. So we'll start with the list. Roger Camargo Palma, congratulations, Dr. Gail. It's a beautiful presentation. Can you study this kind of structures in the moon surface? I guess it will be very interesting to compare with them.
So the question was,
is if you have similar studies in the impact craters in the lunar, where you were showing the Schrödinger crater, and the question is that if you can do similar study in the moon.
Yeah. So yeah, that's a great question. So most of what we know about impact craters come from the moon or Venus, but we can only see the surface. So there are some ideas of how you could image the subsurface, but it's not something that's easily done from satellites. So so there are some ideas of how you could image, but I don't think it's practical. Is my answer. There was actually some ideas of like if you could put on the moon and have like some kind of almost like a cannon where you project something out, and then you could look at the velocity of the subsurface. But yeah, it's not very practical.
Okay. Anna Nila, how did you decide where to drill? Was it related to the seismic lines?
Yes. So we decided where to drill. Initially, we wanted to drill more sites because there's so much excitement about what we could learn. But because of financial reasons, we could only drill one place. And so we decided that the peak ring was the most interesting feature because it had never been sampled on Earth. And so we chose the location where the peak ring was the shallowest. And that was based on the seismic reflection data.
Okay. Frank Rock asks why the circular gravity signature or the gravity anomaly is discontinuous in the north, it's interrupted.
Yes. So we think the circular feature is disrupted because of pre-existing topography that's actually not related to the impact. So we know that there was this big basin to the northeast, and actually we have the opposite thing to the northwest. We think there was a large basement high. So we think these two features is what's disrupting the gravity.
Oh, okay. Why it has been difficult to map the melt sheet? It seems a very large structure, and why it has been difficult to map it?
Yeah, so the question is, how can you map it? So we've been able to map it before by this low frequency reflector. But the problem is we actually only have one profile in the central basin. So the center of the crater is at the coastline. And it's a very shallow water platform that exists now. So the closest we could get a ship was in about 25 kilometers, 20 to 25 kilometers from the center of the crater, where the water depth was only 20 meters. So that's the real problem. Yeah. So the upcoming survey will use a smaller ship, the Justo Sierra, and that's why we can get in shallower.
Okay. Marcela Elizalde asked, actually it's a general question, why there is no volcanic activity in Yucatan?
Why is there no volcanic activity in the Yucatan? So usually there's volcanic activity because of tectonics, right? So there's no subduction zone close to the Yucatan. So I'd say that's why.
It's an interesting question. And Joel Enriquez asks, what is the probability of having another large impact? Will something similar happen again?
Yeah, so we think an impact of that size could happen about every, I'm trying to think of, I've had this in my previous talks, it's about every 100 million years. Is that about right, Jaime?
Yes, yeah, more or less. Small impacts are more frequent, but large impacts are relatively rare.
Yeah, but yeah, about once every 100 million years. So, I mean, it could happen, but they're rare. Yeah.
And Enrique Barbosa asks if there is evidence for this, is there evidence in other parts of the planet about the extinction and the effects of the impact?
Yeah, so the boundary can be mapped throughout the world. So it was actually discovered in Italy. is where that clay layer and the iridium was discovered. But there's sections that are found throughout the world.
Yes, yes, you actually showed a map with the boundary sites, and they are all over. And there are greetings and congratulations from many different different parts in Mexico and the US, including Yucatan, which is nice. And Mary Lee Verdugo asks, is it possible to know where the coastline was at the time? Or is it possible to reconstruct the coastline at the bathymetry?
Yeah.
I suppose it's at the time of the impact.
Yeah, no, there are some attempts to do that. And what's being used are a lot of the wells that are in the Gulf of Mexico, give you some idea of what the water depths were in the past, and then mapping on land. We know that it was a shallow water platform where the impact happened. But yeah, the question is, where was the coastline? That's a little harder, but there are some ideas. It's not something I'm working on, but I've seen images. Yeah.
Yes. Well, it's perhaps it was to the south of the peak of this peak ring area because of the inclination, the regional inclination of the Yucatan platform.
Yeah, I was going to say I have an image that someone just shared me. Let me see. Can I share one more image? Can I share? Oh. Can you see that?
Yes.
So I'm trying to think what this is showing though. So this is showing what the topography was like. So here's the crater, but I'm not quite sure where the coastline is on this. I think it's pretty far back. I think that's what the yellow is showing.
Yes.
Okay, I'll stop sharing.
Oh, but it's actually a very nice reconstruction map. Is it possible to use this technique? I suppose is the full waving version in oil exploration?
Yes, that's where it's really developed, was in oil exploration.
Okay, and well, you already mentioned the next survey, but Jesus Villegas asked what are the new projects?
Yeah, so that's the big project we'd like to do, is to drill into the melt sheet, because that's something, it was just sampled briefly by some of the Pemex wells, but just only a little bit. So it'd be exciting to see the melt sheet. And also something I didn't present in this project was there's a lot of work that's been done looking at the recovery of life. And so there are places where that record is probably better preserved. And I think where the melt sheet was could be a very interesting place to see how life recovered near this hydrothermal system.
Yes. Well, actually, thanks for this question. We have been studying the Chicxulub impact for a long time. And what is interesting is that every time we do a new study, we find new questions. So it will keep us busy for, I don't know. many more years. And actually, we take this opportunity to invite you, if to all of the students, if you want to get involved, you can study here in Mexico, in the university, and also in the University of Texas. Actually, we have several of our students in Austin. And well, thanks again for all the questions, and because of the time constraints, we will now thank GAIL for the very interesting presentation. And we have congratulations and greetings from many different parts, from Yucatan, from Mérida, from Cuernavaca, from Guerrero, from Colombia, from Austin, and another one from the Faculty of Engineering in the Universidad Central de Colombia in Bogotá. Well, thanks very much. It's always a pleasure that you can accompany us in this conference series. Well, thanks again, Gail. We really very much enjoyed the presentation, and it's very interesting to see the new results and the amazing high resolution you have in the new studies. We invite you to the next presentation next week. It will be about the generation of the continental crust by Arturo Gómez Tuena from UNAM in Juriquilla. It's at the same time. And we would like also to take the opportunity to recognize the contributions of the many colleagues. We have lost a large number of friends and colleagues in the past months. So we take the opportunity to say hello to the families and friends. And well, with this, thanks again, Gail, and I will give the microphone to our president of the UNAM Foundation, Dionisio Meade. Muchas gracias nuevamente a todos y felicitaciones a Gail por el estudio, y les invitamos a la siguiente conferencia el próximo martes sobre la construcción de la corteza continental, a cargo de Arturo Gómez Tuena de la Universidad de la UNAM en Juriquilla. Y le pasamos la palabra a nuestro presidente Dionisio Meade, y muchas gracias a todos.
Muchas gracias, Jaime. Muchas gracias a la presentación que nos hizo favor de hacer Gail Christensen. Realmente muy interesante y pues muy aleccionadora de ese momento crucial, ese momento tan trascendente que se vivió con la caída del meteorito en Chicxulub. Yo creo que es un acierto que hayamos propiciado este encuentro, este consorcio de universidades que se suman al divulgar el avance de la ciencia y que tiene el mérito, además, en este caso, de que consta de presentaciones de investigaciones en curso. Eso le da un mérito adicional y hace que todos participen de cuál es el state of the art respecto a las investigaciones que se están haciendo, por ejemplo, en este caso, para conocer cuál fue la evolución de la caída de un meteorito de esta dimensión y cuál fue su impacto en el planeta. Nosotros hemos pensado que el principal motivo que debiera animar nuestras actividades en este año es justamente reflexionar sobre cómo adecuarnos a esta nueva realidad. Y yo creo que conocer el planeta, conocer su funcionamiento, conocer su historia, conocer el impacto que ha habido de eventos como el que hoy se nos menciona, nos da la posibilidad de conocer mejor nuestro planeta. Y al conocerlo mejor, hoy que hay conciencia de que debemos de tener un mucho mayor cuidado de este lugar, que es la casa para todos, que es nuestro espacio común, logramos también irnos adecuando y irnos centrando mejor en cómo enfrentar esta nueva realidad. Para quienes no tomaban en serio el cambio climático, lo que está ocurriendo ahora, pues es una lección de que este es un espacio de reflexión al que nos tenemos que adecuar. Cuando vemos lo que aquí se nos presenta y se aprecia cómo se ha construido el planeta y cuáles han sido los elementos que han impactado más su trayectoria y su evolución, nos permiten anticipar otras reacciones, otros estudios, otras investigaciones que nos vayan permitiendo conocerlo mejor y que nos vayan permitiendo adecuarnos mejor a esta nueva realidad. Queremos de nuevo agradecer a Jaime Urrutia que le dé espacio a la Fundación UNAM, que le dé espacio a la universidad para sumarse en este esfuerzo formidable que está significando, además inédito, la constitución de este consorcio en el que tantos especialistas, tantos académicos, tantos universitarios pueden participar para conocer mejor. Yo creo que lo que aquí nos decía él, de que hay muchos interesados que han seguido esta presentación, tanto de México, tanto de Estados Unidos, tanto de Yucatán, tanto como de otros países, pues nos ilustra y nos entusiasma de que este esfuerzo inédito puede dar resultados todavía mucho mejores. Agradecemos por eso su participación, agradecemos a todos esos centros universitarios que se van uniendo a este consorcio, en esta oportunidad en particular a la NUYES, que hoy forma parte ya de nuestro consorcio y que habrá de generar en su red de universidades todavía un espacio de mayor difusión y participación. La próxima vez escucharemos a un especialista de la universidad, pero habrá que ver si es posible que algunos de los investigadores, algunos de los académicos de alguna de las universidades que configuran la NUYES se suman también, no solo como auditorios, sino como presentadores, como quienes participan también en estos esfuerzos de divulgación y de investigación. Muchas gracias a todos, gracias Jaime, gracias GAIL por tu presentación y gracias sobre todo a quienes nos escuchan. A ellos está destinado este esfuerzo fundamental y queremos motivar con estas presentaciones un mucho mayor interés en la ciencia, en la investigación. Ellos son quienes van a construir en el futuro un mundo mejor, un mundo más dominado, un mundo más conocido y un mundo que nos permita a todos vivir mejor. Muchas gracias de nuevo y quedamos emplazados para la próxima semana.
Thanks.